I would like now to solve a concrete problem involving Bessel functions, and that is the problem of a variable mass oscillator. You have a block attached to a spring, but this block has got some mass loss properties. Say it's made of dry ice, so it's going to be losing mass at a certain rate. Let's say the mass is m0 plus r0 t, where m0 is the mass at time 0 and r0 is less than 0, which means that as time progresses the mass keeps reducing. And let's assume also that the mass rate loss is very small, so there is some meaning we can associate to infinite time so that we can do the asymptotics of the Bessel functions in this example. Now, the Sturm-Liouville theorem allows us to write the most general equation expressible in terms of Bessel's equation as that, where x to the r is the new function that occurs multiplying the y double prime term, so that the derivative of that term is rx to the r minus 1, and that gets associated to the y prime term. And the y term, let's say, has got some power of s. If this is a very specific kind of a problem which can be reduced, it can be shown to a Bessel-like solution, and that solution is some power alpha times the Bessel function and the Neumann function. Alpha here is dependent on the value r, where r is a number here, and gamma, which is the exponent that occurs inside the parenthesis of the Bessel function or the Neumann function, is given like that. Lambda, the eigenvalue, which occurs in the inside of the argument, is given like this. And lastly, the order of the Bessel or the Neumann function is given in that fashion. If a is less than 0, you apply the transformation. J goes to the modified Bessel function I nu, and the Neumann function goes to the modified Bessel function K nu. So that's the basic result we have, and we can use that result at some appropriate point of solving this problem. But the first steps involved in solving this problem are kind of independent of any of those things. You have to use Newton's second law. Be careful, don't use F equals ma. Instead use the external force is equal to the rate of change of linear momentum. In fact, Newton never wrote F equals ma. Newton wrote dp by dt. According to Newton, force is equal to the time rate of change of the quantity of motion, is what he called the momentum. So if you use Newton's original second law, well, the external force is just the spring force, which is negative kx. So now we have a very nice differential equation. The momentum is just the mass times velocity, and mass does depend on time, so this allows us a more general type of differential equation. By the way, this is how you also solve problems involving rockets, because rockets do change their mass. So if you expand this out, I'm going to end up getting mass as a function of time, which is m0 plus r0 t, times the rate of change of velocity, which is acceleration, so I'll write that as x double dot, plus this time I differentiate with respect to mass, and I'll just get r0, differentiate with respect to time, the mass, so I get r0, and then velocity, which is x dot, and I'll bring the kx to this side, plus kx equals 0. That looks tantalizingly close to what we have here, except the term multiplying y double prime, or y double dot in this case, is not something that looks like a function of so by the way, the map you have to make here is that y is the same as x, and prime is the same as x is the same as time. So it's rather confusing. What we call y here now becomes x, and what we call x here now becomes time. But you notice that the term multiplying y double prime has got only a power of x. It does not have a power of x plus a constant. So we have to make a scaling transformation. Let's call the scaled version of time tau. Okay, so tau is equal to m naught plus r naught t. Not a big deal. It's just a notion of massive time. Hope it doesn't bother you too much. Under this assumption of massive time, I'm going to define my prime as dx by d tau. So x dot is going to be dx by d tau dt, which can be written as dx by d tau times d tau by dt using the chain rule. So I get r naught x prime. Similarly, x double dot is going to be r naught squared x double prime. So our ODE now becomes r naught squared tau x double prime, because now tau is that, plus r naught squared, because I'm getting a r naught again when I write x dot in terms of x prime, plus kx equal to 0. Now this looks a lot like our standard mascot. So in this case, r naught squared is just x to the power r, and r naught squared tau is just this. So we can make all kinds of identification. The identifications we make are the following. First what I'll do is, since this r naught squared business occurs in both terms, so I'll divide both sides by r naught squared. So I get tau x double prime plus x prime plus k upon r naught squared x equal to 0. Now that's a one-to-one correspondence. So I have x is the same as tau, y is the same as x, r is the same as 1, because r is what multiplies. So if I have r equals 1 and x equals tau, then tau is what I get here. So I need r equals 1. Once r equal to 1, you're committed to having x to the power r minus 1 or x to the power 0, which is okay because we don't have anything there. But you still have an r, which is 1. So that looks good. Now k over r naught squared, that is simply what we have as a there. Remember, a is a constant, so k over r naught squared should be identified with a. And s simply doesn't exist. We don't have a power of y is equal to x, so this x should not be confused with that x. This y that I have there is actually x, so s should have power 0. Alright, now it's just a matter of mixing and matching. With all these values, I can find out what alpha would be next. Alpha is going to be 1 minus r divided by 2. R is 1, so that's 1 minus 1 divided by 2, or alpha is 0. Gamma, which is this thing next, is 2 minus r, which is 1, plus s divided by 2. So that's half. Next, we have to find out what lambda is. Observe that a is bigger than 0, so we are looking at j's and y's and not i's and k's. So that's a little relief. So I get 2 times the absolute value of a, which is just k over r naught squared, divided by 2 minus 1 plus 0. because r is 1 and s is 0. So that gives me 2 root k over r naught. Now by the way, r naught is positive, so we better put the absolute value here. And nu, r naught is negative since the mass rate is its mass is reducing, and that's the reason why I put the absolute value sign. Lastly, the order of the Bessel function nu is the square root of 1 minus r squared, which is 1 minus 1 squared, minus 4 times b. Now this constant that I've called b, I'm wondering what that is. I think it's 0. So let me just double check my notes to give you what that, oh, the b is what occurs. Okay, there's a more general equation of which this is a particular case. So this is for, in this particular case, b equal to 0. So I just double check my notes. So it's 4 times 0 divided by, so you don't even have b in this setup, divided by 2 minus r, which is 1, plus s, which is 0. So that gives me nu equal to 0. And so that completes the solution to this problem. You may think it's cheating because all we did was look up a standard result, but it does solve the problem, and that's a pretty big deal. So we have x as a function of tau is some linear combination j naught of lambda, which is going to be 2 root k over absolute value of r naught, tau to the power half, plus c2 times y naught, 2 root k over absolute value r naught, tau to the power half. So you may wonder how to decide which is a proper solution and which solution you should not keep. What are the initial conditions? Well, if you're not worried about large times, if you're looking at the solution at any given time, you should keep both solutions. And the reason for this is that as t goes to 0, as tau goes to 0, observe what that means. Tau going to 0 means that the mass is fully evaporated. It actually means that the time goes to infinity. So you will find that this j naught is approximately equal to 1 at that the asymptotics work out to be like that, and y naught goes to infinity as the mass rate goes to 0. So you cannot have this. So for large times at least, this solution doesn't exist, and you just have this. So that makes sense, because as time goes to infinity, or as time becomes large, it makes sense that x of t stops evolving. The spring just stays there completely stretched out or at equilibrium position, because the mass attached to it is gone, it's disappeared. So that seems to make sense. Anyhow, that's the solution to this variable mass problem. And if you're really puzzled by this, don't be. For asymptotic values, this is exactly the same as a damped sine or cosine. So it's a sine or cosine divided by some power of time. So it's going to be pretty strongly damped.